Welcome to another video from Lockdown Electronics with me, Bill, and this time we've got part 6 of our look at oscillators. When I started this series I thought there'd be at least 3, maybe 4. Little surprised we've got to 6, and I've still got some material, so there'll probably be a 7th, maybe an 8th. I'm really not sure about that one, but I was wrong before, so maybe I'll be wrong again. So let's have a look at stability in oscillators this time, and let's have a look at how we make use of a very common component, and that is the crystal. So we're going to look at how we can get our oscillator to be hopefully nice and stable, and the common way of doing that is to use a crystal which has the symbol like so, and here's a photograph of a crystal. This is the one I'm going to use in the circuits a little later on. It's something I recovered from a circuit board, 4.433619 megahertz apparently. So you can see these things can be manufactured to a very precise frequency, and that in itself is probably the subject of half a dozen videos. And there's crystals everywhere. They're in your phone, they're in digital watches, they're in computers. They really are everywhere. Now there are a number of materials that you can actually make a crystal from, although pretty much all of them are made from quartz. Now Rochelle salt is also useful as a crystal because it exhibits the piezoelectric effect, as does quartz. However, it's a great deal softer, and therefore mechanically is nowhere near as strong. Quartz, of course, is essentially the component of glass. It's silica, and it's probably 10 times harder than Rochelle salt, so it's more likely to survive a bit longer. So the piezoelectric effect then occurs when you apply a voltage to the crystal moves. When you take that voltage away, the crystal returns to its original shape, and in doing so it generates a voltage. And depending on how the crystal has been cut, that the frequency at which it does that can be very precisely defined. In other words, its resonant frequency. In the case of the crystal you're looking at here, 4.433619 megahertz to be precise. Now a crystal's got quite a complex equivalent circuit. If you're going to try and model it, you see what you actually get is a coil, a capacitor and a resistor in series, and they're in parallel with another capacitor. Now this video isn't about the subtleties of that, and they're probably well beyond a hobbyist like me. However, I think it doesn't take too much thought to realise that depending on how you connect that kind of circuit up in another circuit, it's going to give you a different response. And so before we get onto the circuits that we're going to look at themselves, we're going to just have a quick look at the difference between a series and parallel resonance, because I think it's tempting to just see the number on the crystal as being the answer. Well, that depends how you use it in the circuit. So if we take a crystal, and if we feed a signal in to one side of it from the signal generator, and we monitor the output on an oscilloscope, as we pass the point of resonance, we'll see a sudden peak in the signal. It's quite marked. Now I'm just using the screen grab function here, but you can see how that signal level, as I sweep backwards and forwards, increases and decreases quite markedly, and that's as we pass the point of resonance. Now my scope's a bit of a blunt instrument for looking at the exact frequency that's going on here, but what we can do is we can do the same thing, and we can look at that on a spectrum analyzer. So recall I said that's the equivalent circuit of a crystal. So if we take a crystal and a small value capacitor, in the case of this plot here I've got a 15 picofarad capacitor, and the purple trace, I've put the 15 picofarad capacitor in series with the crystal, and you can see the resonant point there, which is marker 1. Very specific point where the crystal comes into resonance in series with that capacitor. If I then take exactly the same capacitor and crystal and put them in parallel, so I've changed nothing except instead of wiring them in parallel, they're now in series, we get the blue trace. Now you can see there is a difference between the two markers. One's saying it's 16.059 and the one's saying it's 16.093, but the general point here is not the exact amount, because obviously the value of the capacitor will influence that to a certain extent, because you can pull a crystal like this is the word that's used. My point is that in general a crystal that's in a circuit where it's in series resonance is likely to have a slightly lower frequency than one that's in parallel resonance. Now we'll have a look at a series and a parallel resonance circuit, and my scope doesn't have the resolution to show you the frequency output that accurately, so I just wanted to show you it here on the spectrum analyzer, which can indeed show you that. So just be aware of that. Depending on how it's used, the frequency will be slightly different, bearing in mind we're only talking a small amount here, over 16 million cycles per second. Okay, let's now go on to the first circuit. And so we've got a JFET, and we've got the crystal X1, and it's essentially the component that's providing the feedback from drain to gate, and that feedback allows the circuit to oscillate. And we'll just look at what's going on there. The important thing to note here is the crystal is in series, so this would be a series resonant oscillator. So nice and simple circuit on the breadboard. Can't go too wrong there. Apologies, I've got a 630 volt 1 nanofarad capacitor there, which is a great deal larger than all the other components. You can see the little greenish component, sort of resistor like component. That's the inductor, the 2.2 millihenries. The resistors, if you really want to check what they are, you can work that out from the color codes. The JFET is in the center, and the crystal itself I've just got down at the bottom there with a couple of jumpers to spread it out so I can get the correct spacing between the pins on the board. So that's the circuit. Let's go and have a look at that on the bench. Okay, not a great deal to see on here. Here's the oscillator as described. I'm just taking the signal off here through this little yellow jumper. That's the oscilloscope's ground connection. There's your crystal. So let's apply some power, like so, and there is the signal. It's not the best shaped sine wave ever, but you can see we have indeed got, according to the top right of the display, 4.4363 megahertz, if the scope's frequency measurement is to be believed. So yeah, that's working rather nicely, and that of course is the series resonant crystal. Okay, well, you've seen series resonance circuit, and we were getting a waveform that we could make use of. We'll do a bit better this time. I've quite deliberately tried to use the same sort of style of oscillator, so the comparisons as simple as possible. So here we've still got the same JFET, 2N3819 JFET, and this time you can see the crystal is in parallel with those 247 picofarad capacitors, and if you paid attention to my previous oscillator video, you'll know this looks suspiciously like a Colpitt's oscillator, which indeed it is. And incidentally the 220 picofarad capacitor, which is many times larger than the rest of the circuit, is just a DC blocking capacitor there in series with the crystal. But the crystal is most definitely in parallel with the 247 picofarad capacitors, and bias being provided by the 82k resistor. So on the breadboard, that's almost as simple as last time. The depth of field on the camera means that the capacitors are a little blurred, so I've labelled them up for you, but you can see the 1k and the 100 ohm resistors. I think they're very straightforward to see. The 247 picofarad capacitors there in the centre, the 220s to the right, and the crystal itself is off to the right and connected through the little yellow jumper to ground. So that's the parallel resonant oscillator circuit and how it looks on the breadboard. Let's go and have a look at it in action on the bench. On then to the parallel resonant circuit. The two 47 picofarad capacitors are there. That's the 220. Here we've got the crystal going through to ground there on that jumper. You can see scope here, his arm there, so let's apply power. And we've got something that's a much nicer sine wave this time. As you can see, it's not perfect sine wave, but it's a great deal better than the previous one. And once again, frequency 4.43455 megahertz. Again, that's, you know, the scope is outside of its calibration, so it's something like that. But that's your parallel resonant crystal oscillator using a single JFET. Okay, well, there you've got a couple of FET oscillators in series and parallel resonance. Hopefully it's made some sense. I learnt a great deal myself doing this video, and that's one of the reasons to do these videos, because I like to learn. So for you experts out there, if you spotted a few errors, it'd be great for you to point them out in the comments. I'm always interested in learning. Please bear in mind that, yeah, you know, I'm just a hobbyist, and so there probably are a few errors, but it's been great to be learning along the way. I hope you've learnt something too, and I look forward to seeing you on the next video. Cheers for now.